Hello students, the next three assignments we're going to be dealing with a data structure that's not linear. It's a hierarchical data structure and it's probably one of the most foundational data structures in computer science, and that is trees. So we're going to split this exploration of trees into three assignments. The first assignment, we're going to create the fundamental unit of a tree, which is a tree node. And that's what we are going to do here. We will be creating the component of a tree, which is called a tree node. So we will have a tree node class. And a tree node has got data in the middle. I mean, this is just like pictorial data. And then it's got a left node and it's got a right node, right? So this data, to keep our exploration simple, it's going to be int all the way through assignment 8, 9, and 10. What we're going to focus on is we're going to focus on some of the features like inserting nodes into a tree, deleting nodes from a tree, traversing a tree, and so on and so forth, and keep the data not songs, but just integer. Now, trees also, just like our linked lists, they use a lot of recursion. The reason why recursion is used is because if you take the tree node and we call the root of the tree as root, and that's a node, then the root has a right pointer and a left pointer. And these are potentially also subtrees. So a root points to a node, which is also a root to a subtree. So this kind of representation is intuitively recursive, and most of our methods are going to use recursion. The difference between a node, a tree node, and the linked list node was that the linked list had data here and just one pointer. This has two pointers. The other important thing about our exploration is that we're going to stay with binary trees. So each tree has either 0, in which case it's a leaf node, or it's going to have one node, one leaf node, either right node or a left node, or it will have two child nodes. So the ancestor is called the parent node, and this would be called the child node. And a child node can also be a leaf node, in which case it's a terminal of the tree. We also can measure the height of a binary tree by the number of levels that it has. So for example, I'm going to give this a number. This is at level 0, this is at level 1, this is at level 2, and it's at level 3. So the height of this tree is 1, 2, and 3. Now, so basically the trees that we will be examining are binary trees, in which have 0, 1, or 2 child nodes. We will also, I'm just going to erase all of this. So we will deal with trees that are kept in a sorted order. What do I mean by that? Our trees are going to typically look like, for example, let's say the root node is 5. Then we have all the data items that are less than this are going to be stored in the left branch, and anything that's greater than 5 is going to go, less than 5 is going, and greater than 5 is going to go here. We do not store duplicates. So now here, if you see this, if the number 3 comes in, so the input order is very important. If the input order is 5, 3, and then 1, and then it's 7, and then it's 6 and 9, then 5 is going to be the root of the tree. 3 is less than, so it's going to go here. And then 1 comes along. So we're going to start with 5, go all the way down till we are not able to go any further because there's no, this is a leaf node. And then we know that 1 is less than 3, and here's where 1 is going to be attached. And then now the next node is 7. 7 is greater than 5, so it's going to get attached here. 6 comes along. 6 is less than 7, so here's where 6 goes, and then 9 comes along, and 9 gets attached here. So it is important for us to, if we would like to keep the tree sorted, we also need to have a way in which we can traverse this tree in the sorted order. And one of those that we're going to use in all 3 assignments is called in-order traversal. The way in-order traversal works is that you start with the root and go to the leftmost node because that's likely to be the least node. So keep moving left until you cannot move left anymore. Process that node. So note that while the input order is this, the in-order traversal will give us 1. So process the left node till you cannot process it anymore. Then process the parent node and then go down the child, the right child. So we process 1, we go up to the parent, we get 3. 3 does not have any right shoots, so then we go back to the previous parent, which is 5, and then go down the right path, and then we reach 7. With 7, we have to continue with each node. We recursively do this process. So we are going to move down to the leftmost child. So we come to 6. Nothing else here to process. Come back to the parent, and then go down to the right, and then we come here. So now we have processed these nodes. The tree is kept in the sorted order, and we traverse it in order, and this is the sequence that we get, right? So the in-order traversal is process left, process parent, and then go right. And so because we are processing the parent in the middle, that's why it's called in order, right? So many of these methods have been written for you, but this is an explanation of the algorithm and the background under which, and the presumptions that we are going to use when we work on these assignments. Now, it may also happen that we may get a tree that comes in this following manner: 1, 2, 7, 9, and 10. And then we start here. So this is the root of the tree. 2 is greater than, 7 is greater than 2, and then 9 is greater than 7, and then 10. This kind of structure, while it is a tree structure, here in this case the tree has collapsed to a linear structure. These kind of structures are not efficient because the searching and sorting complexity of this tree is not better, or it is the same as a linear list. The searching and sorting complexity of a binary tree, which is kept in this way, which is called a balanced binary tree, in which the difference between the 2 leaf nodes is at the most less than or equal. It's not greater than 1, right? Here the difference between the leaf nodes is 1, 2, 3, 4. There is literally no structure, no tree structure to this. So in a balanced binary tree, we are able to work on the efficiency of log to the base 2 of n, where n is the number of nodes of the tree. This is our goal, to keep a binary tree which is sorted, which is balanced, so that we're able to use the power of the structure to have better efficiency for searching and sorting. In our assignments, all the trees are going to be kept sorted. So even when we insert a element into the tree, we are going to keep it in a sorted order. So for example, if the next thing that comes in is a 4, then we are going to travel to 3 and put the 4 here, not just put it anywhere. And if we get an 8, then it's going to be greater than 7, less than 9, so it's going to come here. So we are going to keep the tree in sorted order when we insert and when we delete. But insertion and deletions can make the tree unbalanced, and this is the kind of structure that we would like to prevent. So this is an overall view of what we are going to be doing in so I would like to show to you the template. So here is the template in which we construct the tree node, which has got data left and right. We've got routine getters and setters, get the left node, get the right node, set the right and set the right, and add data to the left node, add data to the right node. And then Boolean function, is this a leaf, and so on. Now there are 3 constructors. The important items are the constructors. And as you can see, the default constructor sets this to 0, everything to 0, left and right to null pointer. The custom constructor 1 just sets the data because it doesn't know what the right and left pointers are going to be, so it sets them to null. And the second custom constructor actually has information about the right and left pointers, and therefore it will actually go ahead and set them. Of course, both of them, when both of them are null pointers, we can use this, but when at least one of them has got a value, then we can use this custom constructor. All of these, so the constructors are given to you. So the constructors are given. What you need to do is write the get left and get right functions, set left functions, and add left function. So a lot of the code is given. And then here, what the main program does is it creates a tree by creating nodes using the custom constructor and passing this data value. And then what we're going to do is run the in-order traversal of the tree, starting at the root, which results in having the tree printed. And then the second task that we are going to do after constructing and doing the in-order traversal is searching for a node. And this is searching for the number node. If you found it, say found. If you don't find it, say not found, right? And then inserting a node into the existing tree and then printing the in-order traversal. Your task here is to write the search function. You are given an in-order traversal, you're given an insert function, you need to write the search function. And the output is going to look like this. And your output, once you're done with writing the search function, it should look like this.